that to figure out what I did to the brightness. So we got 5 times closer to the sun, number 1. Does that make it brighter or dimmer from your view? Obviously it's brighter, right? I mean, the closer you get to the sun, the brighter it gets, okay? How many times brighter did it get?
25.
25 times, because you square whatever factor you change the distance by. So the sun would be 5 squared equals 25 times brighter there. So how many watts? Well, what I do to figure out how many watts per square meter, I mean, is the brightness there. It's 1300 at Earth. It's 25 times brighter if you were only 1/5 of an AU from the sun, 5 times closer to the sun, 1/5 as far from the sun. So if it's 1300 watts per square meter at Earth, it's 25 times brighter there. What do I do? 1300 times 25. So you just do that. In your calculator, you would say the answer is 25 times 1300 watts per square meter, whatever that is. So it'd be 100 times brighter would have been what? The 130,000, divide that by 4, whatever. You plug it into your calculator, and that would be how bright it was there. So you just have to figure out by what factor did the brightness change, and then multiply it by whatever it was at Earth, and that would tell you how bright it was at the new location. Yes?
I'm just kind of confused. Can you explain to me why the luminosity doesn't change in that equation?
I can do that, yes, I can do that. As soon as I ask if anybody wants me to say anything more about what we've said so far.
Wait, so the answer is 32.5 thousand watts per...
Whatever 25 times 1300 is, yeah, so, yeah, whatever, in this case, whatever 25 times 1300 is,
Yeah.
and I could do that in my head, but it's too much pressure. So instead, I'll go to Google Calculator.
It's 32.
You did it, huh? Yeah.
You can do it.
Okay, I'll do it. I believe you, and I'm still gonna do it, times 1300. So that's gonna be 32,500 watts per square meter in that location.
If it was 5 times farther,
Yeah.
would you do the same?
I do the same, except instead of, if it's 5 times further, did it get dimmer or brighter?
Dimmer.
Dimmer, so do I still multiply by 25?
You divide.
I divide by 25. I would take 1300 and divide it by 25 to see how bright it was 5 times further from the sun, which, by the way, would put it right around where Jupiter is. So at Jupiter, it would be more like 52 watts per square meter, not nearly as many as it is at Earth. Okay, any other questions about that? So why didn't the luminosity change? Okay, what does the luminosity represent? What is the luminosity?
Brightness.
Careful, brightness is what we see. It's how many watts per square meter at Earth or wherever we're located. And so sometimes we do use brightness and luminosity kind of interchangeably, but let's be careful and not do that here.
Like total energy emitted.
Total energy emitted per what?
Square foot? Or square kilometer?
No.
Meter.
No, brightness is the one that has per square meter in it. So a watt is, what's a watt? Watt is a watt. A watt is a what per what? Joules per second. Energy per time is what power is. Watts are. So this is joules per second per square meter. Luminosity is just plain watts. Joules per second emitted by the entire surface of the sun is its luminosity. The luminosity is the total amount of energy that the sun is emitting every second. Total luminosity, the luminosity, total amount of energy the sun is emitting every second. Does the sun care how close or far you are from it in terms of how much energy it's emitting every second? It does not. The sun doesn't say like, oh, she got closer to me. I better dial down my luminosity so I don't blind her, right? The sun doesn't care. Put another way, the luminosity is an intrinsic property of the sun. It's a property of the sun itself that's independent of where the observer is. So the luminosity stays the same no matter where you observe it from. That's like saying, if I get closer to you, what happens to your weight? Nothing, because your weight is a property of you. It has nothing to do with how close I am to you or not. If I get closer to the sun, what happens to its mass? Nothing. Does that mean nothing we would experience changes? No, we would feel more gravity from it if we got closer to it. We would see more light falling on each square meter of our detectors if we got closer to the sun. But the sun's rate of putting out energy has nothing to do with how near or far we are from it. So luminosity is independent of where we are because it's a property of the sun itself. It's an intrinsic property of the sun itself. Yes?
On the exam, do we need to know the layers of the sun?
Yeah, I have that on the guide, that I want you to know what the layers are of the sun. That, you know, that in other words, if you were flying towards the sun from far away, what's the first layer you'd be passing through? What's the next layer? What's the next layer? What's the next layer? I'll give you a list of the layers, but you have to put them in the right order.
And do we need to know the difference between fusion and fission?
Yeah, you should know that. Yep. Yeah, you should know that. What do nuclear power plants on Earth use? Fission or fusion?
Fission.
Fission, yep. What about, so it's, you know, it's like, oh, which one is it? Oh, well, you know what? I was out with my grandma fishing by the nuclear power plant. You know, I come up with stupid things like that to remember things, right? So fusion is what happens in the sun. Fission is what happens in nuclear power plants on Earth. Now, a goal is to make fusion power on Earth because it would produce a lot more energy for a given amount of fuel than fission does. And if we manage to learn how to fuse hydrogen and get energy out of it on Earth, there's hydrogen everywhere. I mean, you just need water to get hydrogen to do fusion power. And so it would be awesome, but we're not there yet. All we've got is fission power on Earth. So fission involves doing what? Is that making nuclei come together and make bigger ones, or is that taking nuclei and having them split apart into smaller ones? Yeah, fission is splitting apart into smaller ones, whereas fusion is coming together and making bigger ones. Yes?
Could we expect to see a math problem like that?
Yeah, you could. I could give you a math problem. And it would be the kind where, like this one, you don't need to do, you know, like really long involved calculations. If you know what you're doing, you would be able to realize, oh, okay, it would be 25 times brighter if I got 5 times closer to it, or 25 times dimmer if I got 5 times further from it, that sort of thing. So I'm more interested in you being able to make those kinds of relations as opposed to, I tell you the sun's, you know, I wouldn't do something like, you are 6 AU from a star that is 12 times brighter than the sun. How many watts per square meter is the brightness of that star at that location? Because while it's important to be able to plug numbers into calculators and all that sort of thing, insight comes from understanding things like this. What happens if I change something? How many times bigger or smaller does it get? That's actually a bigger intellectual challenge than just plugging a bunch of numbers into a calculator, honestly. So,
And then could we go over some of the other math problems around the mass spectrometry?
if you give me specific examples, yes, like let's do this one, then we certainly can, because it turns out I don't have them memorized. No, that's okay, right. So if somebody wants to give me a specific example, then I'm happy to go over an example, yes. And while we're waiting, does anybody have another question to ask about something? Yes?
Can we do like a math on what?
That's what he said. So some other not math question, because I'm looking for somebody to give me, and you know, and basically in other words, I'm not gonna make one up, you have to read me one that I do, okay? So, yes?
So we should expect short answer math questions.
Yeah, you can have a short answer math question, yeah, of that sort. But this is also the kind of thing that can be multiple choice in that, in other words, I could say if you got 5 times closer to the sun, what would happen to the brightness? Would it be 5 times bigger, 25 times bigger, 5 times smaller, 25 times smaller, a million times bigger, whatever, and then you'd have to know which one to pick, you know, as far as that's concerned.
Was there a different inverse square law, like, for a
Gravity.
different, like, for a different situation?
We saw an inverse square law for gravity.
Was that last unit?
It was last one, yeah. But you know, the thing is with an inverse square law, whatever it is, whatever you do to the distance,
Yeah,
you
it's
square
always the
that to
same.
figure
Yeah,
out what
I just
it
meant
is.
like
Yeah.
for a different situation, not.
Yeah, we met gravity is also an inverse square law. If you got 5 times closer to the sun, the gravitational force from it on you would be 5 squared equals 25 times bigger. Same kind of deal. Mhm. Yes?
In the CNO cycle, can we go over like what a catalyst is?
Yeah, like what do I mean by a catalyst with the CNO cycle? So the CNO cycle is that complicated series of reactions. And here it is in all of its glory. Even I haven't memorized this. So if you said to me, well, what's the entire CNO cycle? I'd be like, I don't know. I'll look it up. But the key is, notice that it starts with carbon 12, and at the very end, it ends with helium-4, the final product that comes out of it, and carbon 12. The carbon 12 got recycled. That's what makes it a catalyst. It got recycled. Something that participates in a series of reactions but doesn't get used up because it gets recycled is a catalyst. And we often talk about catalysts in chemistry, but this is an example of a nuclear catalyst, a catalyst in a nuclear reaction sequence instead of a chemical reaction sequence. Part of the problem with chlorofluorocarbons destroying the ozone layer was that they act as catalysts. They don't get destroyed in those chemical reactions, and so a single CFC molecule can destroy ozone molecule after ozone molecule after ozone molecule. It doesn't just destroy one, it just has a party and destroys many, many ozone molecules. That's part of the problem with it. Yes?
What's the net reaction involved in hydrogen burning via the proton chain?
So first of all, of course, it's hydrogen turns into helium plus energy. And by the net reaction, I mean the overall reaction. How many protons overall go in the net to make that helium nucleus? In other words, here's the helium-4 nucleus that's finally created, okay? Each of these neutrons here used to be a proton. So there are 4 nuclear particles in the helium-4 nucleus. 2 of them are neutrons, but they used to be protons. So in fact, the net reaction is 4 protons makes 1 helium-4 nucleus plus energy, because 2 of those neutrons in the helium-4 used to be protons. If you look at the details here, there are 1, 2, 3, 4, 5, 6 protons that go in, but the reason why the net overall reaction is 4 protons make a helium-4 nucleus is because over here we see that 2 protons fly out. So in other words, 6 go in, 2 come out. So on the whole, only 4 of them have become the helium-4 nucleus. And the other 2 are recycled again. These guys fly out and they're ready to start the cycle again. So the net reaction is 4 protons or 1 H nuclei become 1 helium-4 nucleus plus energy. That's our net reaction. You look like you're not quite buying what I'm selling. Is that true? Or
No, I do. There's just a lot like in this little paragraph So like you covered it, but there's just, I'm trying to read like the rest of it.
Oh, okay, yeah, if you want to, if there's anything else you want to know about it, let's do
yeah.
that too.
How does MC E equals MC squared play a role?
Come into this, right. So if I compare the mass of this helium-4 nucleus right here to the mass of the 4 protons that created it, what do I find? Does the helium-4 have the same mass as the 4 hydrogen that made it up? Does it have less mass? Does it have more mass than the hydrogen that was used to build it? It's less mass by about 0.7%. It has less mass than the hydrogens that built it. What happened to that missing mass? What did it get turned into? Energy. And what formula might I use to say how much energy that mass turned into? E equals mc squared. That's where that comes in. The missing mass, when you multiply it by c squared, is how much energy is coming out of the reaction. And in relativity, one of Einstein's fundamental discoveries is that mass and energy are, in some sense, equivalent to one another. They're different forms of the same underlying thing. And so you can convert mass into energy and energy into mass.
That's the proton.
Yeah, this is the proton-proton chain, where if you give me a lovely oil painting of this, I'll give you some extra credit. It actually doesn't have to be an oil painting, but if you can tell me this whole sequence, I'll give you some extra credit. You don't have to, but I'll give you some.
Draw it out and like that.
Yeah, you gotta tell, yeah, you draw it out, label it, yeah. Tell me all that. Yeah. Mm-hmm. Yep. Yeah. It's worth 3 points of extra credit. So that's nothing to sneeze at, basically. But you don't have to. You know, it's not, you don't lose any points if you don't do it, but you gain some points if you do. I wouldn't stay up all night memorizing that instead of studying other things, but yes.
Do you have to commit to memory to write it, or can we just copy it down?
No, you have to commit it to memory. Yeah, because, I mean, sure, I could copy it down too, you know, but I want you to have actually, to have memorized it essentially, so that then you can go into a bar and win money by betting that you know that whatever, just, you know, that you know how the sun is powered, you know. Because who wouldn't want to know that? I don't see you agreeing with me, but okay, whatever.
Like commits memory, like that whole diagram?
Yeah, right. So, but here's the thing to notice though. Notice that the bottom is just a repeat of the top. So really, in other words, I don't need you to redraw the bottom here. What you could do is draw the first part, the top part of it, right? In other words, you say, okay, 2 protons fuse together and you form this deuterium nucleus because one of the protons turns into a neutron by spitting out a neutrino and a positron. And I don't actually care if you tell me about it annihilating with an electron to produce the gamma rays. You can just tell me about the neutrino and the positron, and I'll be fine with that. So that's step 1. Step 2 is a hydrogen comes in, fuses with the deuterium, and makes helium-3, two protons and 1 neutron, and it spits out a gamma ray. And then it hits another helium-3 that was made the same way and produces a helium-4 plus 2 hydrogen nuclei, 2 protons again. But in other words, you really just need this step, and then you can say it hits another helium-3 that was made the same way. I don't need you to draw the whole bottom, you just say, and then another helium-3 made the same way comes in and does that final step right there. Yes?
So it's 4 hydrogen that turns into 1 helium?
Yep.
And then is there just a lot of hydrogen in the core? Or
There
is
sure
it,
is.
Or is it in a different, like...
No, so where is fusion happening in the sun?
In the core.
In the core only. Most of the sun's fuel, potential fuel, is going to be wasted because the hydrogen in the outer layers of the sun will never get down into the core in order to be used as fuel. So it's kind of like if you have a campfire and you don't stir it, you can have a situation where the center burns out and you got all this unburned wood surrounding. And the sun is kind of like that. It will waste most of its fuel because it will never make it into the core. But despite the fact that the sun will waste about 90% of its fuel, it will never fuse about 90% of its hydrogen, it's still got a lot of hydrogen in the core. I mean, it's converting 600 million tons of hydrogen into helium every second, and it's got so much hydrogen in its core that it can do that for 10 billion years before it runs out. At the rate of 600 million tons every second, it's still got a 10 billion year supply of hydrogen in the core. Why? Because as we have learned, sun big! So it's got a lot of hydrogen to go through.
So is that what it's doing with like the convection that happens in the chromosphere? It's bringing down more fuel to the
It doesn't go to the core. No, the chromosphere is just in the outer layer above the photosphere. There's a convection zone outside the radiative zone, but the thing is that surrounding the core is the sun's radiative zone, and material doesn't move around in there. And so, in other words, this material here never gets down into the core. This hydrogen out there never gets down into the core to get used. This material here, this hydrogen circulates, but it doesn't go all the way down to the core, and so it never gets into the core to serve as fuel. So, kind of like what happens in Vegas stays in Vegas, what happens in the core stays in the core. The stuff outside never gets into the core to be used as fuel. So the sun, as a result, wastes most of its hydrogen into its life. The sun will never burn into helium about 90% of its hydrogen. So it's not very efficient, in other words.
Okay. Could you explain the convection zone and like what all is happening there?
So convection is, what convection means is hotter gas rises and cooler gas sinks. It's the way that a radiator heats a room. A radiator heats a room because the radiator heats the air next to it, and that makes it expand, become less dense than the surrounding air, so it floats up to the ceiling. But when that happens, it is replaced by cooler air coming in from the floor, and very soon you get a situation where you set up what's called a convection cell in the room, where the radiator keeps warming up air that rises to the ceiling, and then that air that was warmed cools down, exchanges energy with its surroundings, heats the rest of the air in the room, and the cool air sinks, goes along the floor, and goes back to the radiator again. In the sun's outer layers, like this, we also have convection, where warm gas heated by energy coming up from below, from the radiative zone, that warm gas, warm plasma really, rises to the surface and cools down and sinks back down again, and the cycle repeats. You have a whole bunch of convection cells in the sun's outer layers where warm plasma is rising, cool plasma is sinking, and in the end, it's transporting energy from deeper down inside the sun up towards the surface. Whereas in the radiative zone, that's not how energy transport happens. In the radiative zone, energy is being transported by the fact that because the core is hotter than, the direction of the core is hotter than the direction away from the core, at any point within the radiative zone, huge numbers of photons are going towards the core and towards the surface, but there's more going towards the surface than there are going towards the core. So on a whole, there's a net outward transport of photons towards the surface away from the core inside the radiative zone. Yes?
Can you explain the parallax a little bit more?
Sure. Yeah, like what's the deal with parallax? I just want to reassure myself that my phone is still happily doing things for the people at home. Yeah, I think so, because it's still zoomed in there, right, and then the button with the black square that says stop recording is still going. Okay. You're welcome, people at home. Okay, so parallax. Parallax is how we measure distances to stars. It's the only direct way we have of measuring distances to stars. And the key is, parallax in general refers to the fact that if you view the same thing from different positions, then it will appear to shift back and forth in front of things that are much further away behind it. So for example, if you hold your thumb out in front of your eyes and you blink left eye, right eye, left eye, right eye, back and forth. Your thumb will be seen in front of something different by your left eye than it is by your right eye. That's parallax. The apparent shifting back and forth of your thumb because your two eyes see it from different points of view is the parallax of your thumb as seen by your eyes. The closer your thumb is to your face, the bigger is the shift in view by your eyes just from the geometry, just from, if you look, here's a nearer pencil and a farther pencil. The lines of sight from the eyes to the nearer pencil shift back and forth more than the farther pencil do. And so the near pencil shifts back and forth between the two eyes more than the farther one does. Without you even having to think about it, your brain takes that information and gives you depth perception. It's the reason why when you've got both your eyes open, you can see the third dimension. You have depth perceptions because your brain, without you even having to think about it, is doing that processing, comparing parallaxes of things seen in your two eyes' field of vision. Our eyes are not far enough apart to see parallax of stars. They're just too far away for us to have any shift in view between our two eyes. But on the other hand, we're riding on spaceship Earth, and as Earth orbits the sun, our point of view shifts. The baseline is twice the distance from Earth to the sun. From one side of Earth's orbit to the other, we shift back and forth by 2 AU, twice the distance from Earth to the sun. And it's still, because stars are so far away, it's still a small shift, but with telescopes we can measure it. And so here's illustrated, here's star A, which would really have to be way further away from this. There's no star that's as close to us compared to the sun as star A here is, but you wouldn't be able to see it if we made stars as far apart as they are, far away from us as they really are. The line of sight from star A, from Earth to star A is different today than it is halfway around the sun 6 months later, and that causes star A to shift a little bit on the sky as Earth orbits the sun. Stars shift back and forth a little bit on the sky as seen from Earth as we orbit the sun because of our changing point of view. So which of these two stars would shift back and forth more, star A or star B? Which one will have a bigger shift back and forth over the course of the year? Star A would. That's like your thumb closer to your eyes. There's a bigger shift in your point of view when you're closer. The angle between these two lines of sight to star A is bigger than the angle between these two lines of sight to star B. The parallax is half the angle by which the star shifts back and forth. So this angle that I'm drawing out here is the parallax for star A. This angle that I'm drawing out right here is the parallax for star B. So the parallax is half the angle by which the star appears to shift back and forth on the sky. And we saw that there's a simple relation that if we use what are called parsecs to measure the distance, those are designed so that the distance in parsecs is just 1 divided by the parallax, where you measure the parallax in arc seconds. So if I had a star that was 10 parsecs away, what would its parallax be in arc seconds? I think I heard the answer. 1/10. Yeah, you just divide. You just divide. So if a star that was 10 parsecs away would have a parallax of 1/10 of an arc second. Notice that's a very small number, right? Because remember that one arc second is 1/3000/600th of a degree. So a star that was 10 parsecs away, which really isn't that far away, astronomically speaking, its parallax would be only 1/36,000th of a degree over the course of the year. It takes very sensitive telescopic measurements to detect a shift back and forth of 1/36,000th of a degree over the course of a year. It's actually twice that shift because the parallax is half the shift. But parallaxes require very sensitive measurements, and that should be just because stars are very, very far away from us. So, is that for you? Any other questions about parallax and what? Yeah.
Wait, so a star that is 10 parsecs away has a parallax of 1/36,000th of a degree?
Of a degree, but that is 1/10 of a second of arc. 1/10 of an arc second.
Yeah, yeah.
Yeah, but since 1 arcsecond is 1/3600th of a degree, a tenth of an arcsecond is 1/10 of that. So in other words, take 3600 multiplied by 10, and that's 36,000. So that'd be only 1/36,000th of a degree shift back and forth in that case. Yes.
Can you go over what neutrinos are and the solar neutrino problem?
Yep. So neutrinos are subatomic particles, just like electrons are, just like protons are, just like neutrons are. They're subatomic particles, particles that are smaller than atoms essentially. And we used to think that they had no mass at all. Now we realize that they have a very small mass. It's not 0, but they have much less mass than electrons do. And they are produced in some nuclear reactions. So for example, in the first step of the proton-proton chain, when a proton turns into a neutron, it spits out a neutrino as part of that reaction. It spits out a neutrino, and what's important about that is, first of all, neutrinos do not interact very strongly with other kinds of matter. So, for example, a neutrino could pass through light years of lead and not be stopped by it. You literally have trillions of neutrinos passing through your body every second, but they're harmless because they do not interact very much with other forms of matter, and so they just pass right on through without causing any harm. Neutrinos formed in the core of the sun pass through the sun without being slowed down. They just go right out to the surface. Takes them about 2.5 minutes to reach the surface. 2.5 seconds or so I meant to say, to reach the surface, and then another 8 minutes or so to reach Earth, 8 minutes, 20 seconds to reach Earth. So while photons created in the sun take hundreds of thousands of years to slowly make their way to the surface because they keep interacting with things on the way out, neutrinos stream out directly from the sun's core into space. And so by observing neutrinos, we can get insight into current conditions inside the sun's core because they're being formed inside the sun's core. We can see how things are inside the sun's core today. And so the solar neutrino problem was that back in the 1960s was when the first neutrino detectors were built, where you get these basically giant tanks of dry cleaning fluid is one thing that works, the type of dry cleaning fluid. Neutrinos hardly interact with other kinds of matter, but that doesn't mean that they don't interact at all. And so if you have a big enough tank of stuff which interacts sometimes with neutrinos, you can start detecting them. The solar neutrino problem was that we only at first detected about 1/3 as many neutrinos coming from the sun's core as were predicted to be coming from the core, based on how fast the sun would have to fuse hydrogen into helium in order to shine as brightly as it does. That was the problem. We weren't seeing enough neutrinos coming from the sun's core. So what's the solution? There's more than one kind of neutrino. And it turns out, we now know, the fact that neutrinos have a little bit of mass also implies that neutrinos of one type can turn into neutrinos of the other types. And so what is now known to be the solution of the solar neutrino problem is, turns out that the kind of neutrinos being formed in the sun, they're called electron-type neutrinos. Those are the kind that the first detectors were able to pick up. About 2/3 of the neutrinos coming from the sun's core turn into the other two types of neutrinos before they reach Earth. And more modern detectors that are able to detect all three types of neutrinos have brought us into agreement. In other words, when we detect all types of neutrinos, we do see the number of neutrinos coming from the sun being equal to what it should be, given how fast nuclear fusion, according to our calculations, should be occurring in the sun's core. So the neutrino problem is no longer a problem, it's been solved. And the solution is that the neutrinos that are formed in the sun's core turn into other types of neutrinos on the way to Earth. Some of them turn into other types of neutrinos on the way to Earth. Which was a bit of a relief, because it would have been really weird if our understanding of fusion inside the sun was that far off. So it's hard to believe that we could be that wrong about it. So it wasn't a huge surprise when we discovered that so-called neutrino oscillations, changing in other types of neutrinos, was the solution to it. It was kind of a relief. It's okay, yeah, we do know physics. Is that good for you? Yes.
Can we do this math problem? I have it pulled up.
Okay.
Suppose that two stars in a binary star system are separated by a distance of 50 million kilometers and are located at a distance of 110 light years from Earth. What is the angular separation of the two stars?
Yeah, we could do that, but an early question here was I going to give you a problem involving, oh, that's angular resolution, yeah, so, okay, yeah, so this is one that I could do that, yeah, okay. So what were the numbers again?
50 million kilometers, that's...
At first I was misinterpreting what you were asking. They're 50 million kilometers apart?
Yep, and located at a distance of 110 light years away.
110 light years
Find
away.
the angular separation.
Yeah. So I could draw a picture here. So here's the two stars. And remind me again, how far apart did you say they were?
50 million kilometers. And also, can we do it so we get answers in degrees and arc seconds?
Sure. So they're 50 million kilometers apart, 50 times 10 to the 6 kilometers apart. And how far away are they from us?
110 light years.
110 light years. Light years away. So here's us, Earth. Now, clearly, this is not to scale. 110 light years is way bigger than 50 million kilometers is. But, so this distance here from Earth to the pair, 110 light years, they're 50 million kilometers apart. What we want to do here is use what's called the small angle formula. And in order to do it, we have to have the separation and their distance in the same units. They both have to be, you could convert this into light years, but this is a tiny fraction of a light year. So what makes a lot more sense is to convert light years into kilometers, okay? So you'd have to look up how many kilometers in a light year. That's a number that I would give you. A light year is approximately, 10 trillion kilometers, 10 to the 13th power kilometers. So if I call that the distance right there, the distance would be 110 light years multiplied by 10 to the 13th power kilometers in 1 light year. It's good to do conversions where you multiply by a ratio that is equal to 1. There are 10 to the 13th kilometers in 1 light year, so that ratio is actually 1. Writing it like that allows us to cancel units so that we don't accidentally, it tells us how to not multiply when we should have divided or divide when we should have multiplied. In other words, I know I have to put light years on the